for a while, thought that neutrinos traveled faster than light. But okay, let's forget about that. The second puzzle was solar neutrinos. There are lots of them. If you hold your thumb up, you'll have 64 billions of them going through your thumb every second. So it's a good thing they don't interact, because in addition to tanning, you would actually be fried if they did. Only nu's are produced in the sun, not the other two flavors, and they're produced through reactions, mostly of fusion of proton-proton, but some other reactions as well. So it's not trivial to calculate the amount that you will get out of the sun, but this was done by a physicist, John Bacall, and it's referred to as a standard solar model. Okay, so then Bacall got hold of a physicist called Ray Davis, and together they realized that if the solar neutrinos interacted with chlorine, it would change the chlorine into argon, and if you could detect the argon, then that would prove that indeed solar neutrinos were hitting your detector. This reaction only works for electron neutrinos. So they got themselves a huge tank, filled it with 615 tons of cleaning fluid, which is the cheapest way to get chlorine. And they just waited, and every month they would extract the argon, and since it was slightly radioactive, they could count the number of atoms that were produced. The only problem was that out of 615 tons, there was only one atom produced per day. It's not very much. And so every month they would extract, and instead of 30, they would find something like 10. And at that point, there were two camps. One camp said, you must be crazy if you believe Davis, how can he possibly extract one atom out of 615 tons? And the other camp said, you must be crazy if you believe Bacall. How can he possibly calculate what comes out of the sun? Who knows what really goes on in the sun? So there we were, and then another experiment came along, the same one that was studying atmospheric neutrinos, Super Kamiokande. They used a different reaction, and in that reaction, an electron neutrino hit an electron in the detector, bounced it off, and then it was detected through its Cherenkov light in the Super Kamiokande detector. Again, this works only for NUI. Now, Super K is very good at computing the neutrino direction from the direction of the observed electron. Also, it can tell you exactly the time at which this event actually happened through their fancy electronics. And so, since they knew the time at which the event happened, they also knew the position of the sun at that point. And they could therefore plot the angle between the direction of the neutrino and the position of the sun at that point. And what they found was that, indeed, if you plotted the angle in 2 dimensions, the largest number of neutrinos, denoted by the white color, came directly from the sun. And so here's a picture of the sun taken from underground with neutrinos. That's pretty fancy. The only thing is you can't do it with an iPhone. You need a big detector for that. So, yes, they came from the sun, but it was still less than expected. And finally, a third experiment came along, this time in Canada, in a nickel mine. The reaction that they used was actually sensitive to all 3 flavors of neutrino. Now, you might say that this is redundant, since only electron neutrinos are produced. Indeed, it was redundant. However, using all 3, they did find the exact numbers predicted by the solar model. The conclusion then is that if you start off with electron neutrinos only, and you need to detect all 3 flavors at the other end, the electron neutrinos must change into nu mu's or nu taus. Okay, and for that, given the distance and the rates and all that, they were able to extract the second mass difference to be about a factor of 5 less than the first one, and that's called the solar mass difference. Okay, and for that, Kajita, the head of Super Kamikande, and Art McDonald, the head of SNO, were awarded last year's Nobel Prize for Physics. Earlier, Davis was also honored, and he got the Nobel Prize for his discovery of solar neutrinos, together with a man called Koshiba, and we'll talk about Koshiba in a couple of minutes. So at this point, two mass difference were obtained and measured, and two of the angles, and it left the third angle to be measured.